So, thanks everyone for coming. My name is Karen Bennett. I'm the regional soil scientist for Region 6 for 3 more days. So this is the accumulation of many years of work, and I really wanted to share it with my colleagues here in the regional office and folks out on the forest, although I'll get another chance to share it with them as well. But this is really a new view of the region. I've learned a lot over the last 5-6 years that I've been working on this, and I think that the goal is to keep learning how to use this mapping tool. So get into it. So basically in 2011, I was working with Dr. Jay Noller at Oregon State University, and the Washington office started talking about terrestrial condition classification, kind of based on what was being done with the watershed condition framework. But we needed a unit to call our landscape unit, you know, not working with watersheds. And Region 6 didn't have it. Many of the other regions had what we call Landtype Association mapping. Region 9 has had it for 20 years, but Region 6 did not have it. So we embarked on this process, which I'll share with you today. So it was Dr. Noller was the key mapper. I was the key instigator and person who showed up at his office every Friday to say, so how you doing? Chris Ringo was our GIS analyst extraordinaire. Jeremy Hobson has been an incredible assistance in mining data and looking at information with the framework of these land type associations, and I'll show you that. And then Sarah Hash was one of our early developers. She's a soil scientist at the Deschutes National Forest. So I say 2011 to 2016 plus because we need to learn how to use this, and we probably need to develop it some more. So what are land form or land type associations, and I'll hopefully by the end of this presentation you'll understand the difference between land form associations and land type associations. But it's basically a mid-level assessment unit. It's a terrestrial mapping that helps organize landscapes with the ideas that if landscapes have the same formative factors, the same geology, the same climates, the same kind of history of geophysical signatures, that they'll behave the same. So you can better learn a portion of an area and then extrapolate it to a larger area. So hopefully we've at least initiated that. And it helps also with a better understanding of the inherent capacity of different landscapes for many things, for erosion, for productivity, for habitat characteristics, and it helps us understand the sensitivity and resilience of that landscape. I think I can use these arrows. There. So just like we have a watershed hierarchy, we have a terrestrial ecological unit hierarchy. The Forest Service uses this naming structure from the global scale to the site scale, and goes from the domain all the way down to a land type phase. Land type and land type phase are what people traditionally think of as a soil survey. And we have 3 of those. We have the soil resource inventory in this region, the state soil geographic information, or the SERGO mapping, that's your county soil surveys. And we have a terrestrial ecological unit inventory, which is what the Forest Service calls a soil survey. So it brings in and kind of melds vegetation and soil information, which any good soil survey would have done anyway. So the Forest Service, through most of the country, uses Bailey's ecoregions, this region, because we had a very collaborative effort between the EPA, USGS, Natural Resource Conservation Service, and the Forest Service, we all worked together to create the EPA ecoregion map. And so that's what we use at this scale, at the continental and regional scale, depending on the level of those ecoregions. That's what we use in this region. And then we have the state soil map that they call StatSco. That's at a scale of 1 to 250,000. So we have 1 to 250,000 as a unit, and then all the way down here at 1 to 63, 360, 1 inch to a mile, or even down to 1 to 12,000, 4 inches to a mile. But we were missing this scale right here. And so that's what this fulfills. It's a mid-level landscape assessment of the region. And I'll be curious to see what people think of this. It's definitely a different view. So here's the ecoregions, just so we're all on the same page. We have the Coast Range.
Same as Omernick, right?
Omernick and EPA, same, yes. So the Klamath Mountains, West Cascades, East Cascades, Blue Mountains, Northern Basin and Range, Columbia Plateau, a little bit of the Rockies poking in here, North Cascades, and the Puget Lowlands. So those are our organizing kind of ecoregions. There's a movement afoot in both the Forest Service and the NRCS to refine these, and that's probably going to happen over the next 3 years, I would say. And some of this information provided that you'll see today will feed that change. So land type associations, we have 2 routes. So this is the new route, the landform associations. This is what people in this region have not really seen before. So this was a effort where we combined geology, morphometric measures, geomorphic processes, and heads-up cartography. And I'll show you what it's like on the next slide, to create what we're calling landform associations. So this is the new term, and I feel like this is the geoecology of the region. And if you understand this, just through our naming structure, you can go out and kind of have a sense of what you might find before you even hit the ground. The other side, the right side of this, is where we bring in modeled potential vegetation, and the ecologists have worked on this over the years. They're currently refining their potential vegetation model, but it brings in the climatic factors, landscape positions, maybe soil attributes if they could find the data, and definitely data from their field plots. And they use the regression model to model vegetation. So when you combine the landform associations and the vegetation, that's when you get the land type associations. And that's the ultimate end product of this that I'll be showing you today. So Dr. Noller created a terrain model to look at different landscape units. I mean, you can just see the diversity just from this itself. You have really smooth slopes, and an anti-dip slope that goes down, another smooth slope, and a dip slope that goes down, giving you really kind of structurally controlled landscape. Versus right here, very highly dissected landscape adjacent to it, and then over here, very smooth. So we use this model to kind of initially define the landscape units. Then we used some morphometrics, some relief, aspect, slope length to look at, are we in high mountains, are we in low mountains? It helped us differentiate some of the landscapes. And then we looked at group geology. The geology map in the raw is very complex, and so we grouped it into 9 different geologic units that kind of are based on whether it's erodible geology or really hard rock or recent sediments that would tell you how that landscape would react. And then Dr. Noller did heads-up digitizing of most of the region, several tens of millions of acres. Heads up digitizing? Well, he literally drew every one of these lines to characterize the different geologies, morphometrics, and geomorphologies that he was seeing in the landscape. And then we created a naming structure, and I'll pass this out for you to look at, because what you're going to see here is the top row is what I'm calling terrain classes. I'll show you what those are on the next slide. And then below that are all the geomorphic processes that occur within that terrain class, and then the itemized actual landform associations below that. So it gives you a way to organize this concept.
Just a quick question about the slide back. So on your group geologies, you said that you identified these groups based on erodibility and some other factors.
Right.
Are you guys, there's actually lots of people that have been doing that, including us. I'm wondering if you guys are going to publish that particular aspect specifically, or maybe as part of the whole package.
Part of the whole package.
Okay.
We're gonna publish this.
Awesome.
Yeah.
Great.
Yeah. So ultimately, this is the area of the region that got mapped. So you can see all national forest land got mapped. That was the goal of the project. Sometimes we went outside, the royal we, meaning Dr. Knoller, went outside and mapped other lands, particularly BLM lands. But some of these private industrial lands up here in northwest Oregon and southwest Washington didn't get mapped, as well as the Columbia River Basin and southeast. But we tried to map all landform associations that went outside the national forest to their maximal extent. So this is what is mapped right now. I had a meeting with NRCS last Friday, and as a result of this mapping, they're interested in mapping the rest of the region so we can have wall-to-wall coverage. They saw real value in having this. So here's the terrain classes. For the folks that are on the webinar, I'll just switch screens right now just to show you the handout that I passed out to the people in this room. But it relates to this slide, the terrain classes. So Emilio, can we switch? No. Okay, I'm not going to do that because it wants me to install another thing. Okay?
Okay.
So we'll go back to the PowerPoint. There is, for the folks that are connected to Adobe Connect, you can actually download this, this document. You can go in and download it for your own use. But basically, it's the classification kind of structure, so you can kind of see how we were approaching this. So we basically have lowlands, these different areas that are in brown, the marine terraces here, and then we have these plains, so sediment areas coming off the base of mountains, fluvial valleys. Then we have a lot of plateaus. These are the flood basalts from eastern Oregon. If we map this would be a lot of plateau as well. The majority of the region is mountains, and there are 53 different landform association designations within that mountain system. So it's mountains, but they're not all equivalent mountains. And then we have the valleys, the dark blue areas that are in here, all these fluvial valleys up here in the glacial terrain. And then we have all this volcanic terrain, which has really never been mapped before. You can bring in like the Esri coverage of volcano points, and it covers some of these, but it doesn't cover all. So this is really a new look at volcanism in the region, including some remnant volcanoes. This one has never been recognized before. and then Rainier, Mount Baker up there. So this, I think, is a new view of the region.
That mountain was never recognized as a volcano.
As a volcano, yeah.
What is it? You don't remember which mountain it is?
I forget the name of it.
The valley is supposed to be purpley, is that right?
The valleys are the dark. Oh yeah, it's purple too here.
Yeah,
those are all valleys.
Your key is off. That's what it's showing.
Okay.
Dark.
Yeah. Okay, so then if you follow this classification structure down, you get to geomorphic processes. So these are the main geomorphic features that shaped this landscape. So you can see that the majority of the backbone of the Cascades is all glacial. And I'll get to what kind of glacial in a minute. But everything that's light blue here has been glaciated in the past. These blue areas are fluvial. We'll talk about them a little bit more. And then the other big feature you see are these orange, yellow, tannish areas that are mass wasting is the dominant geomorphic process happening there. And then these dark brown areas are really structurally controlled, tectonic or really some clear rock bedding structures that are controlling how those landscapes erode. And then, of course, the volcanic processes that are operating. So fluvial processes, I thought this was interesting. Most of these, at this scale, which is 1 to 100,000, most of the fluvial processes are valley bottoms. And hardly any of them are in national forests. They're all outside. Why? Because that's where people like to live. They're all settled, they're all developed. And even if they do come into the national forest, then there's private land that comes into the national forest. So we do have a little bit, like up here, this is the middle fork of the John Day. But I would say, like even over here, another portion of the John Day, that on the national forest system, these are pretty rare. And so to have this and to not have it been developed, but I mean, it's probably been grazed, but these are pretty dim. So I wonder if we should be respecting those and you know, protecting them a little bit more than we are. So highlighting the glacial processes. So when I would say that there's 3 types of glaciation that we've identified. One is purely glacial, these light blue areas. You walk into this landscape and you think U-shaped valley, you know, scoured mountain slopes, glacial valley walls, glacial moraines. I mean, when you're in that landscape, you know you're in that landscape. That starts right up around Detroit Ranger District on the Willamette and goes north. And the farther north you go, the more apparent the glaciation is, and even lots of active glaciers in that area. Matter of fact, the Forest Service has most of the remaining glaciers in the American Northwest or American West, and the Mount Baker, this area up here, Mount Baker and Okanagan have the most in the region. This dark blue area are things that have been glaciated in the past. You can see scours, you can see some formation of cirque, but other processes have taken over now. Some mass wasting, collapse of the mountain, so that you walk into that area, like you walk onto most of the Willamette National Forest, and you're not clear that you're really in a glacial landscape until you find, you know, rounded boulders or cobbles up on the hillside. You can find the signature of the glaciation, but it's not clear to you that it's really been glaciated until you dig into it. And then we have the continental glaciation, the Puget Lobe, of the Cordilleran ice sheet, and I'm not sure, the Okanagan lobe over here. And so you can see most of the Colville National Forest was continental glaciation, a good part of the eastern portion of the Okanagan-Wenatchee National Forest as well. And so on that sheet, you'll see different names that we give to these glacial processes. We call it either alpine ice sheet or glacial scoured if it was from continental glaciation. These alpine areas are actually mountains up, like in the Passaic Wilderness, that were above the level of the ice sheet. So they aren't scoured and flattened like a lot of these areas over to the east in the Colville are, because they stood above the ice sheet itself. But they did have some alpine glaciers on them. And then we use terms like cirque basin, cirqued, ice cap land. You know, the area from Mount Jefferson south had quite an ice cap on it at once, you know, over a mile deep is what people are saying, which really does nice job fracturing the bedrock below it. And so, as you know from our own knowledge of the spring systems, but what Dr. Grant has highlighted, that's really where a lot of our seasoned springs that come out in the Metolius Basin and the Mackenzie Basin are because of that great fracturing of the landscape in under this ice cap land. And then as the glaciers move down the valleys, we have terms like glacial fluvial, glacial lacustrine. Some of the Oso landslide was a glacial lacustrine deposit. We have glacial volcanic and paraglacial, meaning next to but not touched by the glacier. So just to, you know, a visual of what that looks like. Glaciated volcanoes, we still have active glaciers up here. And then this is the ice cap land that's really flattened and scoured. And that ice cap, you know, it moves back and forth any which way. And then you have cirques kind of calving off of this Tim MacArthur rim here. Also cirque basins in some of the high mountains where you had a alpine glacier scouring out, leaving a morainal feature and a lake behind it. And then just highlighting the mass wasting landforms, there's 35 of those. We use terms like dissected or incised, meaning that streams and fluvial erosion, surface erosion, have cut into this landscape. We use terms like collapsed or variegated if the land is hummocky and either dormant earth flow or could be active earth flow, or the whole mountainside has collapsed, such as in Mount St. Helens, the north flank of that collapsing in Lahar. And then we use terms like smooth crusted, where the rock has no bedding structure, so it equally erodes. So there's, you know, it's very smooth-sided mountains. See a lot of those in the Klamath, in the Siskiyou National Forest. So just an example of the collapsed terrain. This is Highway 20 coming over, comes up from Sweet Home and goes over to Tombstone Pass and ultimately to Bend. And this is where the road just kind of roller coasters and slides along. This is mapped as one of those variegated mountainsides. This is what we were calling it. I do want to use the term hummocky because hummocky has the connotations of meaning active landslides. And so we adopted the term variegated, meaning that it's just kind of like varicose veins. You know, it's warty and has texture to it. Anyway, we can change the name. But here's an example of a collapsed mountain up on the Gifford-Pinchot National Forest, a result of the Mount St. Helens Lahar. So what I've been doing the last month is writing descriptions, writing the guidebook to all of these. And so yeah, on our system we'll have every one of these landform associations and their associated vegetation or land types that are associated with them. Every one of them will be defined. And when we define it, we define kind of like what was the geomorphic process that happened out here, how did it affect the land, what kind of habitat, how's the water storage move in that system, and then what kind of soil orders. We're able to mostly get it down to soil orders. And then some idea of, is that land, is this feature, is it abundant on national forest land, abundant, common, limited extent, or rare, just to give people a sense of it. So this would be what the Glacial Valley, this is the Glacial High Mountains landform, and then the Glacial Valley landform, and a little bit of a glaciated volcano sticking in here. And then on the east side, we have mapped things like plateaus or incised plateaus that have started to erode, fluvial valleys, variegated mountains. You know, this, you can see this has come down and blocked this valley at some point, backing up this nice valley here. But probably still feeding into the stream system here as a chronic source of sediment. And then we just talk about each one. So this one particularly talks about the incised plateaus and how they were formed, how they water moves on them, and maybe something about habitat. So every one of these definitions just kind of highlights, it doesn't go through everything every time, it just highlights the features of that. And so this is an example of a plateau over here, and over in the distance, incised plateau in the foreground, and canyons or canyon lands, depending on how extensive they are. So now we'll look at, you know, how did we attach the potential vegetation model. So the ecologists mapped it, as I said, bringing in the climatic, elevational, landscape position factors. And so the result is a potential natural vegetation map that goes from Sitka spruce on the coast, western hemlock, grand fir in the valley, up to Pacific silver fir, mountain hemlock, and then as such across the region. So if you look at this map and think about the Coast Range ecosystem, you know, it basically takes in all of this. But even in the vegetation, you can see how different the Olympic Peninsula is. And if you remember that glaciation map, this was entirely glacial, either glacial scour or glacial outwash, or even some of the Puget lobe came down and left glacial moraines on the sides of the mountains there. And the Coast Range has totally different processes that operated it. So I really question whether they should be in the same ecoregion at all. So we took these potential natural vegetation layers and overlaid them on the landform associations to get land type associations. And then we added the serpentine areas because I thought that those were really important in the type of vegetation that results. And I won't say that every one of these will have the clear serpentine vegetation with the calcium and magnesium imbalance, but they have the potential to. They may be masked by some erosion or landslides, but these are the areas, if you're doing plant surveys, these are the areas you would focus on. And so then we would...
NRCS help pull apart that serpentine distinction, because I remember a couple of years ago that was a difficult one to get a handle on.
So we use the geologic map. That's why I say the signatures may or may not be there because of mixing, but it's a clue. So I tagged them on, so it'll be like a smooth crested mountain serpentine, Port Orford cedar, land type association. So anyway, the land type associations, when you combine them, this is what the regional coverage looks like, and they're really complex units. So we've taken 133 landforms, and with all the veg combination, and it's not all one kind of veg. It could be like, 50% ponderosa pine, Doug fir, or ponderosa pine, Doug fir, and then some other veg in there, but we tried to capture what your primary and secondary types of vegetation are. And then Jeremy did all this data mining. So for every landform, and every landform association is in dark, and then land type association, for every one of those we have what percent of the ecoregion it is, the slope elevation aspect, and then climatic information. We have all the lithology information, hydrology, stream density, sinuosity, stream temperature, slope gradient, stream gradient, and then special habitats, talus, avalanche tracts, wetland steeps. So this is from soil surveys, our SRI, the National Wetland Inventory. This is from our stream surveys. So we have stream surveys in some places, but then we can extrapolate them to similar landforms. And so that's what we did. And then we had some fish habitat, some substrate information. I really wanted to look at, where were we really experiencing very fine sediments moving in these systems, and where did we have boulders or bedrock as the dominant, and could we separate that out by landform association or land type association? So, so this is like the 2016 plus. So I have all this data, but as Leah told me when I started to summarize all this information, she says, Karen, it's a whole career to figure out what that data means, So I'm passing my career on to the next person to figure out how to use all this information. So I'm just going to go through some examples of how would one use this information. So traditionally we use aerial photos. We have better tools, more advanced tools than that. But, if you look at an aerial photo of the National Forest, you see many timber stands. And some people just think about the system as stands and don't really look beyond. They don't maybe feel a need to look beyond because that serves their needs. But if you added our landform associations, which are this black line, it could tell you, something's different about these areas. And then you, take it over and look at your terrain underneath, and then you can understand, wow, that's really flat. So it's this. It's a sharp edge bridge here. Man, that's really dissected. But you don't know anything about it. So with the landform associations, now you know that this is a pumice plateau, 60 feet pumice. This is just dissected mountains. Your glacial line stops about right here. So below that, you're not glaciated. Above that, you are. Here's some ice cap land, glaciated ridges up here. And so this gives you more of a sense of, well, what's going on with this landscape and how does it differ? How is it sensitive or resilient, and how can I manage it? So then if you put on your veg on top of that, you see that within each of these landform associations, you have Douglas fir, western hemlock, going up to grand fir, going up to subalpine fir, and on up into mountain hemlock. But if you look at it through the LTA, you would think, oh, well, this grand fir on this system is really maybe less productive. I mean, it's growing in popcorn pumice, and there's no streams. There's really no water in that system. So this would be a much less productive system than the same vegetation type on these glaciated kind of sides of these mountain slopes where you have talus and accumulation of sediment from the glacial deposition. So this gives you more of a sense of different portions of this landscape really should be treated differently. But when you saw that first photo, it's like 40-acre units everywhere. Really wanted to talk about the difference between the watershed hydrologic unit hierarchy and the terrestrial unit hierarchy, because they're both important and they're both needed, but they help us understand different things. So watersheds, we understand fish distribution, sediment yield, maybe water yield. You know, sometimes if we're in a limestone area or even these fractured ice cap lands, that water that you're finding in your area may really not come from there. It may come from an interbasin transfer, so that's why I have the question mark. And you can think about water quality in a watershed ecological unit. So these purple areas are your watershed. The colored areas are your veg, and the black lines are your land type. So terrestrial units speak more to vegetation, habitat, wildlife movement, maybe fire movement across the landscape. So they really have different roles, and they're really both important. You know, you can see here's all grand fir. So if you're thinking about healthy forests and insect and disease, and we do have problems up here on the slopes of Mount Hood on the grand fir type with insects and disease, and you only manage in a watershed, by watershed, you're not really addressing maybe the forest health issue of these different vegetation types that you find. And then even when you do manage, if you can manage for this whole system, each one of these different landform associations would have a different productivity associated with that vegetation. So we had a big fire in Canyon Creek, you may remember last year. And so what are the tools that our burned area emergency response teams or firefighters, for that matter, have that they can work with? So they have hillshades, they have watershed boundaries, they have streams, but so they have topo maps, they have veg maps. But if you look at that system, Canyon Creek, in terms of the landform associations, so you have really deep sediments here. These are the piedmonts coming off of the mountain slopes. You have a whole area that is slipping and sliding, barricaded slopes. You have angled, angular mountains, really evenly spaced, steep ridges. Then you have the structural, steep dip slope, anti-dip slope here, and a strong back slope here. So very few streams coming off of this side, but this one is highly dissected, constantly contributing debris and sediment to this stream, Sheep Creek. So Sheep Creek here is affected both by this landform, and all of this is glacial deposits, glacial moraines, or what we call paraglacial. So it's boulders and cobbles and unconsolidated sediments. So they were recognizing that they needed to do something to store and sort sediment in this area. And, you know, we're able to understand it better because they used this map. And then at the upper part of the watershed, you have glacial or cirque basin mountains, so scoured to bedrock areas. You're not going to get much sediment off of those. Your sediment's going to come out of here and the stream undercutting this dip slope. So that's some of the uses. And then if you look at the vegetation, you have juniper coming into ponderosa pine, juniper going up to subalpine fir. And each one of those veg types have a different ability to recover and just the productivity of the area. And even actually, so thinking about some of the fire spread into some of these vegetation units will vary by landform. So I have an example of that a little bit later. I just wanted to point out on Nooksack watershed in the Mount Baker Snoqualmie. So again, you have your hillshade with your stream layer and your watershed boundary, and you can see a lot of variability. But if you define it, you have a very wide glacial stream, glacial fluvial stream. So you can tell that, you know, it's not just glaciers that made this, but it's been reworked by the stream system. You have low glacial mountains, so shorter slopes, high glacial mountains up here, so really gaining elevation as you go up in the watershed. But then you have this sticking up in the middle. It's a volcano. So you have metamorphic rocks here. You have extrusive basalts here have a totally different weathering regime. And so is it pinching the channel here, backing things up? Is it forcing the stream over and undercutting this slope? I think those are some of the things that you can think about. And again, if you look at your vegetation, you're going to have a different productivity potential, much lower on the basalt productivity-wise than on your metamorphic terrain, much higher productivity with those metamorphic rocks. So Michael Brown, working on the Blue Mountain restoration team, is using some of these landforms to try to understand the landscape over there. So he shared these next couple of slides with me. So, you know, when you have LiDAR, life's much easier. I'll just say that. But Jay did pretty good mapping the difference between this collapsed straddle mountain here and this ice plateau. I mean,
I actually moved it over a little bit.
Oh, you did? Oh, don't end my story. Anyway,
full disclosure.
I was really impressed.
I didn't have to move it much, just a little bit.
Anyway, but clearly you can see the difference between what's going on in this landform and the smooth slopes of the plateau here that's starting to be incised by overland flow. So Michael then took the first return LiDAR, the tree height information, and laid it on it. And it's all Grand Fir. So if you just use your veg mapping, you might not understand that you have incredible difference in productivity here than you do on your plateau. This area, you know, these collapsed mountains, these barricaded mountains, they're moving sometimes. Sometimes they're dormant, sometimes they're moving. But you rarely see very deep streams developing on it. You don't have that dissected landscape because it starts to dissect and then it undercuts the unstable slope and then it closes again. So you have very tortuous drainages. So it's blocking the underground movement of water and it's backing it up. You have seeps and springs. You have what I call sub-irrigated vegetation. But it's really gets at the productivity. So just separating out the trees over 20 meters high, you can see how much more they are here than up on the plateau. And this is wilderness, so it's not just that we cut them. They just aren't there. But a veg map will show it all as Grand Fir, a potential veg map. But even within, I mean, this is the other beauty of LiDAR, even within this, you can see you have the scarp and then a pocket of deeper soil, another scarp, deeper soil, another scarp, deeper soil. So this, even within these landforms, you can start to tease out where your productivity is really enhanced. And just thinking about what my friend Jim on the Ochoco calls scab stringers. So grasslands and then any of these incisions in this faulted habitat, faulted terrain, that's where your trees are growing because that's where your moisture is being stored. The faults are again disrupting the hydrology and storing moisture on those lands. So Michael, would you like to talk about how you use this with your fire management team and the grizzly fire?
Yeah, I can speak to that a little bit. So Tom DeMeo was also involved in this work. We were part of a long-term assessment team on the grizzly complex. And we framed our management recommendations around Landtype association based on how we could see historical disturbances interacting with physiography, where we have, in this case, canyonlands where the physiography highly regulates disturbance. And then once you're on the plateaus, it's more regulated by fire weather and the availability of fuels. So looking at the weather patterns, we were able to make recommendations to the management team, forecasting where we would expect the greatest risk for fire spread. And based on our recommendations, using these tools, they invested most of their capital to the southern and eastern ends of the fire rather than on the northwest as they were doing before. So I'd like to think that this saved us quite a bit of money and also some resource damage at the same time.
Right. So you often hear fire folks talk about, well, we're going to use these fire breaks, and you know, we're going to put the fire break on the ridge, and so this perhaps provides alternatives. You know, catching the fire as it comes up onto this plateau is probably easier than catching it on a steep, narrow ridge, and maybe safer as well. And I think the other recommendation you had when you were talking to me about this is that, you know, we do a lot of fire line contingency construction, and it often results in some significant resource damage. But if you can make these decisions about where the fire is likely to move the fastest across the landscape, where you have these vegetation types on landforms that won't transmit fire, you have a better ability to reduce that kind of damage that we see from firefighting, fire suppression.
And if I can add to that, part of the purpose of these long-term assessments is in sharing risk with the line officer and the fire management team. So we can make some of these recommendations based on whatever the best available science is, and that provides them a lot more comfort in making decisions and not throwing everything in the world at it. They can have an informed basis for their decisions about how they're allocating resources and where their contingencies are. Another important point on this is, it's hard to see here, but in the small writing in the diagram in the middle, we're finding that fire wasn't spreading in the subalpine fir. It was only spreading in the grand fir, white fir. So we were able to look at the spread models from the last several days and apply that as a predictive indicator. So again, they can focus their efforts where the greatest risk is. So excellent tools for that, I think, in the future.
Thanks. So here's another maybe potential, but the fisheries folks have mapped bull trout habitat. Bull trout's a threatened and endangered fish species. And so I zoomed into the Mount Baker and Olympic National Forest. And so what we did was looked at, well, what landforms are these moving through? And can we calculate stream miles per landform? And make the assumption that if they're there, then they're in similar landforms. So for instance, you know, they're all through this glacial drainage here, but maybe they're not going into some of the others that have all the same similar characteristics. So if you're thinking about bull trout recovery, those would be some of the first places to check out. I mean, maybe it's blocked, maybe there's some either human or natural reasons that bull trout are not getting up into these areas, like up Okanagan over here. But maybe they're just extirpated from there, and that since it has some of the features that the habitat has where they are, you could be successful in reintroducing them into those areas. So the coding is you know, from brownish through green to blue for least appropriate landforms to most appropriate in the blue. So if you just focus on these dark and darker blue areas, those might be your highest recovery potential. So I sent this to the fisheries bios. I mean, it's a tool. Maybe it can be useful, but I thought we'd share it. And then one of our ecologists, Kim Mellon McLean, has been developing a goshawk and a white-headed woodpecker model. And so she put these landform associations in as one of the components to evaluate. And sure enough, she found that 16 out of the 68 landform associations in the Blue Mountains were significant. 80% in red, 70%, 60, and 50% in green as being goshawk habitat. And so they're using that as one of the bases of the model. Same thing with white-headed woodpecker. They found 11 of the 68 were appropriate for white-headed woodpecker, and some of them very significantly identified. And then within that, because we have this combination of landform and vegetation, then we can isolate it even more down to the types of vegetation that these birds use within that. So this is just showing the ponderosa pine plant communities. They use more than that, but I just wanted to identify the ponderosa pine. I did this yesterday. I'm not sure what it means, but we calculated stream density from NetMap. I don't know if you're all familiar with NetMap. It's Lee Benda's product from Earth System Institute. We wanted a consistent stream layer. If you look at the NHD mapping, it's different quad by quad by quad. So I thought it wouldn't be fair to use that. So we used Lee Benda's model, which has more consistent stream mapping. One of the things that was really, really curious to me, one of the landforms that came out with the highest stream density, lava flows, because of the crenulation in the flows. And it's obviously using landscape features, and it needs to be vetted. But anyway, I thought this was kind of interesting. I mean, no wonder we don't send any fish money down here to the Fremont Wainema.
The water's underground.
The water's underground, yeah. It's a very, very volcanic terrain, highly porous system, lots of wonderful seeps and springs throughout there. But anyway, this is for the 2016 plus people to figure out. And then just thinking about chronic sediment sources, these variegated and collapsed landslides. I showed that picture of Highway 20. Well, that landslide is going down into the Middle Santiam River, and it keeps getting undercut. So it's a chronic source of very fine sediment to the system. So is that true of all these others? And if we're thinking about like sediment issues with water quality, should we have one issue, like this beautiful Deschutes River going through a lava flow that basically has no sediment? I mean, this is a really pristine kind of stream versus a stream that runs through marine terraces and dunal habitat that's constantly grabbing sediment and shifting. I mean, this stream can basically go wherever it wants, and so you have a whole sediment bottom to this stream that you won't have in some of the harder rock, angulate, or dissected areas, or some of the lava flow areas. So I think that we can really start to think about, should we be less prescriptive, singularly prescriptive in our regulations, or should we try to make them match how the landscape is responding? So the Nature Conservancy with their land facet mapping, and Josh Lawler, who has also worked on that process, people are thinking about what they call hedge bedding, like making sure that you conserve some of these unique features. Not particularly because of the vegetation that's on them now, because these geophysical features will evolve differently. They'll change differently. And so if we can preserve each of them, we have an opportunity to learn about that particular system and how it responds to climate change, for instance. And so I did a really quick analysis, and basically we're adequately, the Forest Service on National Forest lands is adequately protecting 50% of all the landforms, and adequately means over 20% of that landform is protected. What's really, wilderness, here, wilderness, inventory, roads list, or research natural areas. We also looked at it by Wild and Scenic River, but I'm not sure of the protective quality of those. What's really interesting is one of our most abundant landforms, which is these incised plateaus, has only a little over 11% of it is protected. And, we protect rock, snow, and ice, lots of our glacial landscapes, landscapes that are very aesthetic, and some of these less aesthetic ones are often have less protection. And then if you think about what's common on national forests, what's limited, and what's rare, should we be protecting all of those? It's rare on national forests, but we should look outside our bounds and see if it's protected on other landscapes. So this isn't a complete analysis. It's just what I found. Okay, so fun facts. What do you think is the most, give me the top 4 geophysically most diverse forests in Region 6? The Rogue. You think it's number 1?
I'm going to say Olympics from just what I saw on some of the maps.
Okay.
Even though it's the tiniest.
Willamette, Rogue, Okanagan, Wenatchee. It is big. This totally surprised me. Well, Whitman's not there. Neither is the Olympic. Neither is, what did you say? Neither is the Willamette. The most diverse forest, wait for it, Fremont, Wainema, because it goes from the glaciated highlands all the way out to lacustrine, basin and range, so
inches of rain to
yeah,
6.
yeah, incredibly diverse forest. It has land types that no other forest has.
And you said there's 133, oh, sorry.
Go ahead.
133 land types?
Landform associations, 133. Yeah, so it has almost half of them, right?
Yeah.
I'm not supposed to put the math. Maybe third. Anyway, anyway, second is the Rogue River Siskiyou, really pretty diverse. Third, Okanagan, Wenatchee. And fourth, Malheur. Right. Yeah, really interesting. So, okay, what are the least diverse national forests? Olympic, Umatilla, Siuslaw. No. Siuslaw, yeah, I didn't think it was, I worked there for 20 years. I didn't think it was so not diverse, but evidently. The Colville is the least. Yeah. I'm not sure if we got tired of mapping by the time we got to the Colville. But really, glaciers do a lot of damage. Continental ice sheets, they kind of just flatten everything, right? Yeah. So second, Siuslaw and Columbia River Gorge tie, and Umpqua and Umatilla third. Yeah.
Oh, wow.
So, okay. Well, fun facts. So that's the mapping that we've been doing, and what the plan was, and I actually told you I'd have this for you today, but I didn't, and I won't, is that we really want to put this on ArcGIS Online and have it so that you can look at the whole region, you can hover over an area, and it shows you where that land type or that landform shows up anywhere in the region, and then you click on it, and the description of it comes up, the fun facts come up about it. And so, and then you can zoom in, you can cut your project area, all of that kind of thing. So that is our intent, and Jeremy Hobson, who's our DRM guy, is hopefully going to build that over the next couple months. I'm like the eternal optimist. I met with him last week. I'm like, so you can do it by next week, right? So sometimes reality hits.
Until that's done, and it's the data
T drive? So the data is on the T drive. Okay. All of these descriptions will be on the O drive.
Can you give us the path to the T drive?
Yes, as soon as I clean it up, so you don't see my many renditions of this mapping, we'll send out the path. But, I need to talk with Jeremy and Dorothy about a permanent place, because right now it's in a collaborative folder, so I need to find a permanent home for it. Yeah.
Is it available for folks outside of the Forest Service?
I think it will be. I'm working with researchers, so I think they want to publish it before they release the data. So then it will.
What
But
is-
our intent is to do that over the next, by July, I'd say.
So published by, or what's sort of that timeline, you think?
Submitted to a journal by July, so as soon as it's submitted, it can be released.
And you mentioned NRCS is doing the mapping on the rest of the state.
Right,
The 2 states.
right.
Any idea on what the timing of that might be?
They're very interested in moving ahead on that, so
But
it will
haven't,
probably take a couple of years for it to happen, but because they're revising their because everybody has their own language, right? So they have what they call major land resource area boundaries, or landscape LRUs, land resource units, which are equivalent to our ecoregions and land types. Because they're revising that, they want to get this done for that, and they're trying to get that done in the next couple of years. So they were really interested in their planners using this kind of information for things like the Two Chiefs Award. They have this whole east side objective to reduce fire risk. So they're thinking this would be a great tool to say where are the priority areas.
So a couple of years ago, you talked to us about writing up, and maybe it was the descriptions, and I don't know if you were going to publish that as a GTR or how that was,
Right.
all the information.
Right. That's the intent. Is we're going to put it all on ArcGIS Online and then turn that into an electronic GTR, because it's over 1,000 pages. Yeah. So we don't really want people printing it out.
All that description will be attached to ArcGIS?
Yeah.
Okay, fantastic.
Yep. Mm-hmm. Mm-hmm.
So I just want to recognize that we have folks from Oregon DEQ here, Gene Foster, who's here, Ryan Mitchie, and Peter.
Brian.
So just acknowledge that their presence and very much interested in. So back on the data mining, so you are making connections for hydrology and then some water quality attributes. So what data sources are you using for the temperature? Are you pulling out of our databases? Or
Yeah, it's all of our databases. So the temperature are the, I believe there's 81 watersheds that Lewis has used to be the unmanaged watersheds. So so we're using that data. And then we're using the stream survey data that Katie Sears manages to get at substrates and sinuosity and thankful with, yeah, it'll be interesting. I mean, the data will be there. How it's going to be used, how it's going to be interpreted is really, for us, as we use it, I think we'll make more and more connections and observations.
Yeah, and that was a thought that I had on writing the guidebook, the landform associations and the Landtype. The resource issues that come up for each of those, and then the management applications and other versions of Landtype mapping, we've seen kind of interpretation.
Right.
Do you foresee that coming
So,
down?
So we just put all of the soil resource inventories for all national forests up online, and the interpretations are there. So we need to give Jeremy a little bit of a break because he's been going almost as harder than I have over the last 3 weeks. But that they're available to be mined as well.
At that scale, at the SRI scale.
They are.
Okay.
They are, right. So it's suitability for timber, different logging methods, quality for range, water yield. Yeah, we're going to get like hydrologic class.
Right.
That'll be part of the initial database, but all of those, now that they're electronic, can be mined. Yep. Yep.
So guides for mining would be the thing to do.
Pardon me?
Well, develop some case studies, guides for mining, pulling information into an application, and doing case experiments, how to use it, like what you've done.
Yeah, we're using it on the Blue Mountain restoration team to identify or make correlations about pattern and patch size, species distribution, and where to best locate close forest refugia, site productivity, and fire refugia.
Yeah, so that made me think, we're also, I think the decision has been made, you can maybe correct me, to use it as the basis for forest plan revision, that everyone is working with the same ecological unit base.
I don't know that that's a hard and fast, but definitely strong leaning that way.
Okay.
No, big capital decisions have been made.
Okay.
I had a comment more than a question, unless I misheard you. Region 9, you said it has used Landtype Association for 20 years. Seems like we could learn a lot from them on how they've applied it, where it has worked and hasn't. I know we have different situations here and different landforms, but just is there anything pulled together on where they've had their successes and haven't, and how they've used it? Do they have a...
So I believe that Dave Cleland is on the line. And Dave, if you hit *6, maybe you can talk, because he's the one that mapped those and has been using them with National Forest all the time. Dave, are you on the line? Yeah, it's 7 o'clock in the east. Yeah, maybe not. Anyway.
It just seems like, I guess my comment is, we can learn from them and from
Right.
them if they've been doing it 20 years.
That's right.
Yeah.
I agree.
Karen, we do have some questions from Adobe Connect.
Okay.
Yeah, the first one is, who do we talk to about getting corrections done to the LTA feature?
There's some errors.
I would say whoever gets my job. I mean, we definitely have to come up with I think that's a really important question, because, I mean, even in writing these and looking around the region, it's like, I would have mapped that differently, right? So the more we use it, the finer we can identify these areas. And so if the LTA is not correct, then that can be changed. But we did develop it so that, because we knew a new potential veg model was coming. So we developed it so that you could incorporate that new model and rerun the LTAs. Or if you have, your favorite veg model, you can incorporate that and rerun it as well.
So will there be like a version number? So if I were to use it in a habitat model for something, and I say, okay, I used version 1.5, and then run it again 3 years later, and that's like version 2.5 by that time or something,
Yeah, that's a good idea. Yeah, we need to come up with some way of how do people feedback, and data steward, and I'm all about crowdsourcing. I mean, it'd be great to get like pictures of every one of these units and put those on the RTIS online, and that's for all the folks in the field that get the opportunity to visit these. Mark? Oh, is there another question?
Yes, we do. How will this compare to or complement local land type association mapping, like what Mr. Shank has done here on the Willamette?
This is a question of scale, right? Doug Shank has refined the soil resource inventory, which was mapped at a scale of 1 inch to a mile, and 1 to 63,000. So this is a scale above that. And so the idea is that as we refine our soil resource inventories, and we have a crew doing that on the Willamette right now, as we refine those inventories, we tier to these, or we adjust these with what we really find on the landscape. But that's a difference in scale.
Okay, I do have one more. Anything revealed between LTA groupings and climate change vulnerability? Wondering how this layer looks draped onto the R6 Draghi soil index at a coarse scale. Hopefully that makes sense.
So I think the question was, how,
I thought it was on the right-hand side.
Go back to your smaller screen
Yeah.
or something.
do I just do this?
Not really.
Anyway, I think the question was, how does the land types, how will they be used to assess climate change, the risk of climate change, and how does it relate to the droughty soil map that was just created? So if that was the question, I'll answer that question anyway. So the idea of, trying to map geomorphic processes. So for instance, like glacial scoured landscapes, you know that there's going to be bedrock exposed, there's going to be talus slopes, there's going to be, fines mixed in on the lower portions of the slope. So the upper portions of these glacial units, which have really coarse, cobbly soil, those do well, and they can produce vegetation when you have good precip. But as our precip starts to change and we get reduced winter precip and definitely more droughty summer precip, we're going to start to see those landscapes as more vulnerable and less able to support the vegetation. So the landform gives you a clue to the soil forming factors. I mean, it's really a scale to look at soil forming factors because it talks about your parent material and your climate zones, the LTAs, climate zones, parent materials, type of organism that's on the site, and relief and time. So it's really an indicator of the types of soils you would expect to find on that landscape. So is it a one-to-one correlation? That droughty soil map was made from a finer scale soil information, so it is what it is. I don't know if it will exactly tier to this, but we can use this to inform it for future renditions. One more question in here.
So I'm wondering about the relationship to the ecological site descriptions. Are those a similar approach at a finer scale or a very different approach?
Very similar approach, actually, at a finer scale, yeah. Okay. So the ecological site descriptions will come in somewhere around 1 to 12,000 or 1 to 24,000. And they're looking specifically at soil-plant geomorphic relationships on a finer scale. So where I have a glacial valley, they'll pick up where the moraine deposits are, where the talus slopes are, and those will all have different ecological site descriptions based on the soil-plant relationship, not geomorphic relationship. Okay, we are over. So I really thank all of my colleagues in here for coming, and glad I get to share this information before I walk out the door.
Yay!
Walk out the door.
Yeah. So thanks everyone on the phone as well.